Hello, welcome back to the third lesson on vector algebra. In this lesson, we are going to consider vector or cross products of two vectors. Now, in many applications of vectors in real life, in mathematics, physics, and engineering, there is a need to find a vector that is orthogonal to two given vectors. Now, before we discuss vector or cross products of two vectors, let's quickly talk about the real life applications of cross products of two vectors. We are saying that if we take engineering, for example, one of the applications of cross products of two vectors is for robotics and computer aided design. In computer aided design and robotics, the cross product is used to calculate the orientation of objects in 3D space, which is essential in robotics and computer aided design, that is CAD CAD. Also, one of the applications of cross products of two vectors in this same field is structural analysis. So in structural analysis, cross products is used to calculate the moment of inertia and stress on beams and other structural elements. Also, in physics application, for example, the magnetic fields, the cross product is used to calculate the magnetic force on a charged particle or a current carrying wire. Also, in other applications such as computer graphics, the cross product is used to calculate lighting effects and shading in 3D graphics. Also, in navigation and orientation, the cross product is used in navigation systems such as GPS to calculate orientation and positions. And the last one that we would like to talk about is medical imaging. The cross product is used in medical imaging techniques such as MRI and CT scans to reconstruct images of the body. Alright, so in this lesson, we will discuss a new type of vector multiplication that can be used for this purpose. We are seeing that in a three-dimensional right angle or right-handed rectangular coordinate system, when the positive x-axis is rotated counterclockwise into the positive y-axis, a right-handed or standard screw would advance in the direction of the positive x-axis. Now let's look at an image in this page. We are seeing that in the right-handed coordinate system, if the thumb of the right hand points in the direction of the positive x-axis, then what will happen is that the fingers are curled in the direction away from the positive, and that's what is happening here. All the fingers are curled away from the positive x-axis towards the positive y-axis, and that is what is illustrating here. Now let me take it again. We are saying that in a right-handed coordinate system, the thumb of the right hand points in the direction of the positive x-axis. Sorry, the thumb of the right hand points in the direction of the positive z-axis, and that is what we are talking about here. Again, the fingers, when the fingers are also curled in the direction away from the positive x-axis towards the y-axis, and that is what the fingers are showing here. So exactly the same thing happening. A screw, all the other parts of the screw points to the positive y-axis. All the other parts of the screw point towards the positive y-axis. Alright. Okay, now let's look at the definition here. The vector or the cross product of two vectors, let's say vector A and B, is denoted by A cross B or vector A cross vector B, and it is defined by A cross B equals magnitude of vector A times magnitude of vector B times sine of the angle times n, where n represents the unit vector. So we are saying that the theta represents the angle between these two vectors, such that the angle is greater than or equal to 0, or the angle is less than or equal to 180 degrees. Alright. N is a unit vector that is perpendicular, so we are talking about this vector. So this vector is the unit vector that is perpendicular to the two vectors, of course, vector A and vector B, such that the vector A and B and N form a right-handed system. So as you can see clearly, we have our unit vector here, which is perpendicular to the two given vectors A and B. And in that, when we extend the line downwards here, we could see that the right-handed system is formed where the right-handed system rotated from A, so from A, rotated from A, so here to B, and it moves in the direction of the unit vector, which is what the N. So it moves from the direction of the unit vector here. So it moves from here to the vector B. So what we are trying to say again is that if either vector A equals to 0 or vector B is equal to 0, then the angle is not defined. So if there is a vector for A and it's 0 and B is also 0, then the angle between the two vectors is not defined in this case. And for that matter, the cross product of these two vectors will be equal to a 0 vector because there is no angle defined in this case. Okay, so if we have the two vectors A and B as usual, A1I, A2J, and A3K representing the components of the first vector A, and B1I, B2J, and B3K being the components of the second vector B respectively, then the cross product is given as this one. So here we make use of determinants. And for that matter, if we will use the rule which is plus, minus, plus from the concept of matrices, determinants of matrices. So in this case, if we take I, then we would delete all elements in the row of I and in the column of I and the row of I. So it will be left with A2, A3, B2, B3, and that is what you have here. So A2, A3, B2, B3. Then the next one is minus. So minus, and then the next letter is J. So we come back here, we delete all the elements beneath J. So these are the elements beneath J, and in the right of J2. So this one will go and this one will go. And for that matter, we will have A1, A3. So A1, A3, B1, B3. So you have B1, B3. And that is what you have here. Then the next one is plus. So plus K. We delete all entries beneath K. So we delete all entries here. And then to the right of K, then we will have A1, A2. Of course, that is what you have here. B1, B2. Okay, exactly that is what we have. Now, if you want to find the determinant, we know that the determinant is this one, the diagonal entries here. So you have A2 times B3 minus B2 times B3 all times I for the first one here. Then for the second one, we have minus already. So we will bring the minus sign here. Then you multiply A1 by A3. So you have A1 times B3, sorry, minus A3 times B1. and that is what you have here. And for the last one too, A1 times B2 minus A2 times B1 times K. Alright, so whenever a question of such nature is given, what it is required of you is to form your matrices from the components of the vectors given. So in this case, we are given this, and we are given that for the second vector, and this one too. Okay, so we just form our matrices I, J, K. The first one, you have A1, A2, A3. So A1, A2, A3. For the second one, you have B1, B2, and B3. Then we form our corresponding components as well here. Okay, now let's take a question. If a vector A equals 2, 1, negative 1, and B equals negative 3, 4, 1, evaluate the A cross B and B cross A. Please don't forget that A cross B is not commutative or is not equal to B cross A. What we are saying that the result for A cross B will not be the same as B cross A. So shouldn't forget it. Alright, so we have our question here for that matter before our IJQ for the determinant matrix. And that we have 2, 1, negative 1 here for the first one, and then negative 3, 4, 1 for the second one. In that case, we take I using the rule plus minus plus. The first one, we delete all entries to the right of I and beneath I. So we left with 1, negative 1, 4, 1. So 1, negative 1, 4, 1. Alright, for the I, we are still with the rule. Then the second one is for J, which is minus. So minus here. We delete all entries beneath J. That is 1 and 4. And to the right of J2. So we left with 2, negative 1, negative 3, 1. And that is what we have here. And for K, it's plus. So plus K, which we have delete this beneath the K and to the left of K. So we have 2, 1 and negative 3, 4. Alright, so when we multiply 1 times 1 is 1 minus, so in this case, where we've gotten to now, let me show a quick calculation over here. 1 times 1 is 1 minus into brackets 4 times negative 1, which is negative 4 for the first one, which is I. So because this one is negative times negative, you have 1 plus 4, and that's why we have this one here. Then the next one is minus. So J into brackets 2 times 1, which is 2, minus negative 3 times negative 1 gives us positive 3. So the final result for this, okay, so the first one was I, and then the second one is K. So for K, we have 2 times 4, which is 8, minus negative 3 times 1, which is negative 3. So we will have 5I, and then here we are going to get negative 1. And negative J times negative 1 will give us positive J. And that's why we have this one here. And then negative times negative gives us positive 3. So you have 11K. So plus 11K. And that's what we have over here. Now B cross A. So the same approach that we use here, the answers will be different because I've already said that A cross B and B cross A will not result to the same answer. Okay, so we have delete entries beneath this, and you have 4, 1, 1, negative 1, and that's what we have here. And for the second one, delete, do the same thing here. So we have negative 3, 1, 2, negative 1, and that is what we have. Still the rule holds. And then here for the K, we have this one to be deleted, and we're left with negative 3, 4, 2, 1. Okay, so that is the, so 4 times negative 1 is a negative 4, minus 1 times 1 is even a negative 1. Okay, and then for the second one, so you have negative 3 times negative 1 giving us positive 3, minus 2 times 1 giving us 2, and then negative 3 times 3 giving us negative 3, minus 2 times 4 giving us 8. So we subtract this one from, get negative 5i, negative j, negative 11k. So you can clearly see that the result for the first one and the second one are not the same, and therefore we conclude that when the cross product of two vectors a and b is not the same as the cross product of b when we interchange the vectors. Now, properties of vector products. Let's quickly talk about properties of vector products. So if A cross B is a vector which is orthogonal to both A and B, then what happens? So if A is a vector which is orthogonal to, then it means that their cross product will also be equal to 0. Okay, now for mutually perpendicular unit vectors, for example, we have I cross I equals J cross J, which is equal to K cross K. So in this movement, if we cross I to I, it will be the same as crossing J to J, the same as K to K, which results to 0. I dot J is, so in this case, I dot J is equal to K. And then, so if we say, now the reason why we are saying that this one is equal to 0 is that this is I cross J. So I cross J giving us K. And then J cross K. So J cross K 2 also giving us what? I. Do you get it? I cross J giving us K. J cross K giving us I. And then K cross I also giving us G. And for that matter, it results to 0. Alright. It is always true that the vector product is not commutative as we showed earlier on. Therefore, A cross B is equal to negative B cross A, and it follows that J cross I is equal to negative K. If they are not the same, then we are saying that J cross I, when we make an inverse movement from here, J cross I, then we are going to have negative what? K. We are making an inverse movement. So we are going to have negative K. And also K cross J. So we are coming back here. So K cross J also giving us negative I. And then the last one is I cross K. So making an inverse movement giving us negative J. For that matter, the cross product is not commutative. Now the distributive property of vector products or addition. We are seeing also here that if A and B, if A, B, and C are any three vectors and there is a scalar lambda, then A cross B plus C is the same as A cross B plus A cross B. A cross C, sorry, so here will be C. And there is a scalar, if there is a scalar here, then the scalar times A cross B is the same as A cross the scalar times B. So this is the distributive property of vector products over addition. The next property is also saying that if we have A and B being two non-zero vectors, then the cross product between the two is a zero vector if and only if A and B are parallel to or collinear to each other, as we said in our lesson 2. The same thing is happening here. If the two vectors are collinear or parallel, then their cross product is also a zero vector, and for that matter too, the angle is also 0. Now we are also saying that In particular, A cross B is a zero vector, and also A cross the negative of A is also a zero vector. Since in the first situation, the angle is what? 0, and in the second one, too, the angle is what? 180 degrees, making the value of sine to be 0. Alright. Unit vector perpendicular to two vectors. This is another most interesting aspect of cross products. Unit vectors perpendicular to two given vectors. Now we are seeing that the unit vector normal to the plane of two given vectors, or unit vectors are perpendicular to two given vectors. If A and B are two non-zero vectors or non-parallel vectors, meaning they are not collinear, and the angle between the two vectors, then the cross product of the two vectors, or there is an angle between the two vectors, then the cross product between the two vectors is giving us the magnitude of vector A times the magnitude of vector B sine theta. Now we will prove to this why it is so, times the perpendicular unit vector, or the unit vector perpendicular to the two given vectors, as we illustrated in our first situation, where we say this one being A and here to be B, and there is an angle between them, a unit vector perpendicular to the two vectors. So the n is the unit vector that is perpendicular. So this line is perpendicular to these two vectors, or this this vector A and this vector B too as well. Now the unit vector is if n equals 1, or unit vector, the magnitude of a unit vector is equal to 1. For that matter, when we multiply 1 by the whole of this, we are going to be left with this one. Or in other words, if we uh, if we divide, we know that from 1 and 2, n equals to A cross B on magnitude of A cross B. That is for the first one. Okay. Now, if this one, we are saying that the magnitude of A cross B is equal to this. Or we are saying that if n is a unit vector to both A and B, then this one is not there. And for that matter, the magnitude of A cross B will be equal to this. So from equation 1 and equation 2, when we equate equation 1 to equation 2, then we can say that the unit vector n is equal to A cross B over the magnitude of A cross B. Okay, so now let's take a question. Find the unit vector orthogonal to the plane containing the vectors, this one and this. So as I said earlier on, we need to find the cross product. The first thing is to find the cross product between the two. In that case, if we use the first approach on how to find the cross product between two vectors, then we are going to resort to this as our answer. And we are saying that the unit vector perpendicular to this one is also given by A cross B, or magnitude of A cross B. That is what we have over here. And for that matter, if we have already found for A cross B, which is this case, the answer over here, then we need to find the magnitude of A cross B. This is giving us negative 40 on 40 all squared plus negative 15 all squared plus 15 all squared. So the final result is what we have here, which is 582. So the whole of this times this will give us this one back. So we can rewrite this one as the one shown over here. Okay, let's take another example. Find the magnitude of A cross B. The first thing to do is to find A cross B. Here, so A cross B can be found by using the determinant approach. So arranging this one, as I said earlier on, We delete all entries to the right and then beneath. So we have 1, 1, negative 1, 3. And the row is negative 1, positive or plus, minus, plus. So we will have the first one here. And the second one is minus. So minus, we delete all entries to this. And to that, we have 0, 1, 1, 3. That's what we have here. For the last one, delete this one too. And this, so we have 0, 1, 1, negative 1 for the last one. So when we multiply this one, we are going to get 3 minus negative 1 times 1 will give us negative 1. But there is minus there already, so it give us positive. So for the first one, we have this. And for the next one, so we have 3 times 0, which is 0, minus 1 times 1, which is negative 1. So negative times negative 1 will give us positive. So we have positive G. And then the last one, 0 times negative 1 is 0. Minus 1 times 1 giving us negative 1. So we have negative K. For that method, the cross product between these two is 4I plus J minus K. Now, the next thing is to find the magnitude. So square root of 4 squared plus 1 squared minus 1 squared. And that gives us root 3 root 2 as our final result. The next question is to find a unit vector perpendicular to each of the vectors a plus b and a minus b, where a vector a equals to this, vector b equals to that. So the first thing is to find a plus b and a minus b in that case. Okay, so when you find the addition of a and b, you have this, and then a minus b, so we have that. Now the next thing to find the cross products of these two, a plus b, which is this one, and a minus b, which is this. So as usual, we arrange them using the determinant approach, and that we have our final result here. The next thing is to find the magnitude, and the magnitude of this is 6 squared plus 2 squared, and that gives us 2 root 10. And therefore the unit vector is giving us the vector over its magnitude. So 6 a plus 2k over the magnitude, which is 2 root 10, which is the same as 1 on 2 root 10 times 6 j plus 2k. So we can share this one together, and we have 6j on 2 root 10 plus 2k on 2 root 10. Alright, so that is what we have. Note that there are two perpendicular directions to any plane, and for that, another unit vector that is also perpendicular to this will be negative of this, negative of that, but that will be a consequence of this when the first one is being negated and the second one becomes positive. What we are trying to say is that there are two perpendicular directions to any plane. So if there is a plane here towards this, then the required opposite one will be here. If there is a vector in a plane towards this place, there is another one too, which is also opposite to that one. And that we are seeing that if there is a cross product of a plus b minus b, then the opposite side will be a minus b cross a plus b. So where the second one will be negated, and then the first one will be negated, and the second one will be the addition. Of course, we make change of signs. Angle between two vectors. If there is an angle between two vectors, let's say the angle is theta, and the angle is greater than or equal to 0 but less than or equal to pi, which is 180. Then by definition, we are saying that the cross product between these two vectors is equal to a magnitude of a times magnitude of b sine theta on times n, where n is the unit vector. So when we take the magnitude of this, we are going to have magnitude of this a cross b equals a magnitude of a times magnitude of b sine theta. Since the magnitude of a unit vector is also unit or is 1. That is what you are trying to see. So the magnitude of a unit vector is also 1. And 1 times the whole of this also results to the same thing as well as the first one that we have over here. And therefore, if you want to find the angle, then we will divide here by sine theta, we divide here too. So if you want to find the angle, we divide magnitude of A times magnitude of B. So this one will cancel this and we have magnitude of A, magnitude of B. So we have sine theta will be equal to A cross B over magnitude of A times magnitude of B. Alright. But we are seeing here also that if the angle is 180 on 2, of course, which is 90, and then sine 92 is 1. So sine 90, you can check this one on the calculator. Sine 90 is 1. For that matter, 1 times this will give us this one again. So we are saying that now we should take notice of it. If the angle between the two vectors is 90 degrees, now what will happen is that the sine of the angle will give us 1. And for that matter, the cross product will be equal to magnitude of A times magnitude of B. It means that the angle is the two lines are also perpendicular in this case. Okay, the two vectors are perpendicular in this case. So area of a triangle. Okay, so the next one that we want to talk about is area of a triangle using cross products. Now, in this part of our lesson, we are going to find the area of a triangle using the cross products concept or a concept of cross products. Here, we are saying that if vector A and B are representing or be the adjacent side of a triangle. So in this case, we have a triangle ACD, and with triangle ACD, vector A and vector B are representing the adjacent sides of that triangle. Then we are saying that we can find the area of this triangle by the concept of cross products. Now from the triangle ABC, the area is given as half of AB AB dot CD. So area of the triangle ABC equals half AB dot CD. But we know that from the figure, from the line AB is equal to vector B, and that is what you have here. And also CD, line CD, which is the height of the triangle, equals magnitude of A sine theta. Why? From the concept of Pythagoras theorem, sine theta is opposite over hypotenuse. So when we take triangle ACD, then sine theta equals to the height of the triangle, which is CD, on the magnitude of vector A, which is the hypotenuse of the triangle. And for that matter, when you multiply here by magnitude of A, here too by magnitude of A, then by simplification, you can say that CD is equal to magnitude of A sine theta, and that is what we have here. Now we are going to substitute this magnitude of A and this one too here. So we are going to, now we have our ABC or area of triangle ABC to be half of this one. Moreover, the magnitude of the cross product of A and B is equal to magnitude of B times magnitude of A sine theta. For that matter, the whole of this side here is equal to magnitude of A cross B. And so A, magnitude of A cross B, we will use that one to replace this side. And clearly we can see that the area of triangle ABC is equal to half times the magnitude of A cross B. Okay, now let's look at an example. In this example, we are to find the area of a triangle with vertices, this and that. Now we know that AB, so when we find AB, AB is equal to OB minus OA. For that matter, when you subtract OB, which is negative 2, 5, negative 1, subtract OA from, sorry, so we have the 18 to be 1, 4, 6. So negative 2 minus 1 will give us negative 3. 5 minus 4 will give us 1. So plus 1. Okay, let me put them in component form. So this one will give us 1. The negative 1 minus 6 will also give us negative 7. So writing this in terms of I, G, and K will be equal to negative 3I plus J minus 7K. Alright, so the vector AB gives us this one. Now let's find vector AC as well. So AC too, we do the same thing. OC minus OA. So we have C to be 1, negative 1, 1 minus A, which is 1, 4, 6. Now I'm writing the answer here. So 1 minus 1 will give us 0. To me that part is gone. Then negative 1, negative 4 give me negative 5. And then the last one is 1 minus 6 giving me negative 5. For that matter, writing this in terms of I, J, and K will give me the I part is 0, so it's not part here. So you have negative 5 J plus, sorry, this is already negative, so negative 5 K for line AC. Okay, so that is why we have the answer here for the first one, and then the second one we have it here. So now the area of the triangle AC is equal to half of AB cross AC. For that matter, we need to find AB cross AC by using the determinant approach, and that's from the concept of determinants. This is the final answer for this one. Now, magnitude. So the final result of this, we find the magnitude of it, which is 5 root 82. So therefore, the area is equal to half times 5 root 82, and that gives us 5 on 2. So 5 times 1 giving us 5 on 2 root 82 units as our final answer. Again, area of a parallelogram. If A and B represent the adjacent sides of a parallelogram as shown here, so these are the adjacent sides of this. Of course, this side is also a opposite side of parallelogram R, so this one is also B. Okay, what we are trying to say is that the area of the parallelogram ABC is equal to AB dot DE. Of course, AB, so AB dot DE. So this one times the height of the parallelogram, which is DE. But AB is from the diagram, AB is represented with the vector B small letter b, and then DE is also from the concept of Pythagoras theorem. DE, which is the height, is sine theta is equal to DE on the magnitude of A, and therefore here by magnitude of A, here too by magnitude of A, we will say that DE is equal to magnitude of A sine theta. Therefore, we will have our final result as a magnitude of A sine theta. And therefore, the area of a parallelogram is magnitude of B times magnitude of A sine theta, which is also equal to A magnitude of A cos B. For that matter, the area of a parallelogram using the cross product concept, is equal to magnitude of A cross B. Now let's look at an example. In this example, we are to find the area of parallelogram whose adjacent sides are given as this. So straight away, we find our A cross B by using the determinant approach. So we have our final result as this. Then we find the magnitude of this final result, and that is as root of 3 squared plus negative 4 squared plus negative 5 squared, given as 5 root 2. So this 5 root 2 is the final result for the area of a parallelogram. Now there is a proof here. Okay, we are to prove that the area of a quadrilateral ABCD is half of AC cross BD, where AC and BD are its diagonals. Alright. Now let's say this is a quadrilateral. Why is it that the area is equal to half of AC cross BD, magnitude of AC cross BD? Now let's check something here. We know that area of quadrilateral ABC can be partitioned into two. First of all, we will just find the area of triangle ABC. So ABC, so the whole of this side A, B, and C. So this is triangle. Let's call this triangle B. Triangle A. Plus area of triangle ACD, which is ACD. Let's call this one as triangle B. Now we know that the area of triangle ABC is the same as AB cross AC. AB cross AC. So that is what you have here, half of AB cross AC. And for the second one too, we have it as AC cross AD. So AC cross AD. So we need to be very careful. This one is AB cross AC. For the second one, we have it AC cross AD. Alright. Now we know that we can factor half and AC out. Here are the common ones we see here. So half out, AC is here, another AC is here. So we have it outside times. Now we have negative AB. Why are we having negative AB? So we have negative AB in the sense that we are moving towards the opposite direction. So negative AB for the second one. So that is what we are talking for the first one rather. And then plus AD. So for the first one, moving towards this one is negative for AB. So negative of AB gives us this one. And for that matter, we can say that half of AC times negative AB plus D. Moreover, negative AB is the same as BA. So when we move towards the negative direction, which is the negative of AB, which is also BA. So we are talking about this. So plus AD. And for that matter, BA plus AD gives us BD. Now let's check that one. So BA, where is BA plus AD? So BA plus AD gives us BD. So it means that if I move from B to A, we are moving towards the opposite direction and AD. So BA towards the opposite direction or the negative vector here, which is BD plus AD is the same as me moving from B to D, will give me BD. And that is what we have here. So we have proved why this one is equal to half of AC plus BD. Thank you, and don't forget to subscribe to our channel. Alright, so now let's talk about scalar triple products. Under scalar triple products, we are saying that if we have a vector A, which is equal to A1I plus A2J plus A3K, and vector B, B1I, B2J, and B3K. And we have another vector which is C1I plus C2J plus C3J. Any three vectors in 3D space. Then the triple product of these vectors is giving us A dot into bracket B cross C. Right. So this is called a scalar triple product of A, B, and C. Here we are saying that it's not necessary to compute the dot product and cross product to evaluate a scalar triple product. The value can be obtained directly from the formula using this. So what we are saying that it is not necessarily for you to compute the dot product and then the cross product to evaluate the scalar triple product for a case like the one we have here. Because we have the dot product and the cross product, it doesn't necessarily mean we have to tackle this one first and then the results we dot it with A. But what we are saying is that there's an easier way for us to do this by using the determinant approach. So for the first one, fix the triples or the triple pair of the vector A followed by vector B and then C. Of course, it will result the same answer. Now let's prove this a small proof here. We are seeing that why this one is acceptable formula to use for a scalar triple product. Suppose we maintain vector A and then we cross vector B to C. Then by the rule plus minus plus from the determinant of a matrix, we are going to have B2, B3, C2, C3, I, B1, B3, C1, C3, J plus B1, B2, C1, C2K. From this one, when we tackle or when we tackle A1, means we are deleting all entries to the right of A1 and maintaining this one. That's why we have B2, B3, C2, C3 for the first one. So when we target A22, we delete entries in the row of A2 and beneath it. So we left with B1, B3, C1, C3 as usual. Moreover, if you are to tackle A32, we will delete all entries to the right and entries beneath it. So it will be left with B1, B2, C1, C2 for the last one, in this case, the K. And so we are saying that if we dot A vector A2, the cross products of B and C, then this is the result that we are going to have. And of course, we know that the triplets for the vector A is A1, A2, A3. For that matter, the first determinant is going to have A1 multiplying, first determinant is going to be multiplied by A1 minus A2 times plus A3 times the third one, of course. So if you look carefully, you could see that this is the same as A2, A1, A2, A3, taking the first place for the determinants, and then B1, B2 taking the second place, and then the C1, C2 taking the last place for this case. Okay. Now we want to talk about geometrical interpretation of scalar triple products. In this case, we are saying that let vector A, B, and C be three non-coplanar vectors. So consider a parallelepiped having coterminous edges OA, OB, and OC such that OA is small letter A, OB small letter B, and OC small letter C. We are saying that the cross product is a vector perpendicular to the plane containing A and B. And we will let phi be the angle between C and then cross product of A and C. Now let's check the diagram here. So this is the diagram we are talking about. So we have a cross product of vector A and vector B, which is perpendicular to this side too. And that is what we illustrated about, that is what we said about here. Here we are seeing that these are OA, OB, and OC are co-terminus edges. So let's check OA. So OA is this one, OB is this one, then OC. These are called coterminous edges of the vector. So these are the coterminous, these are the coterminous edges. So this one, then this. So A, B, C are the coterminous edges of the parallelepiped. Okay. And so we are saying that the cross product of A and B, or A cross B, is a vector which is also perpendicular to the plane containing A and B, and phi be the angle between C and then A and B. So A cross B is the line or the vector which is perpendicular to this one. And for that matter, we are also saying that since A cross B is perpendicular to A, we are saying that phi is the angle between this one, between the cross product of A and B and C. And of course, we have the same phi here because of alternate angle property. So for alternate angle property, that is what is happening. So phi, same thing here. So that's why we have phi here and phi here from the concept of alternate angles. Okay. Moreover, we are saying that we are to let CL. Now let's check CL. CL is the height, also perpendicular to OADB. So OADB. So let's look at the bottom here. OADB is the base of the parallelepiped, and that CL is perpendicular to the base OADB. And for that matter, OL becomes the height of the parallelepiped. Then CL and A cross B are also perpendicular to the same plane. Of course, that is true. This one is perpendicular to the plane. CL is also perpendicular to the plane. And therefore, we can see that CL is parallel to A cross B. And that is true. So this side that we see here, the height of the parallelepiped is also perpendicular to A cross B. So this line here and this line here are all parallel to each other. We are also seeing that angle OCL, so the angle at C, is also represented as phi in a right angle triangle OCL. So we have our OCL here. So now let's check it again for a better understanding. We have our OCL here. Now let me remove OCL for clarity purpose. So we have this, one here. And then we have our phi 2 here, which is the angle. Now we are seeing that in the right triangle OCL, the CL, which is the height, is equal to the magnitude of C times cos of the phi, which is the angle. So cos of the phi, which is the angle. Why are we saying that? From the concept of Pythagoras theorem, we are saying that cos cos phi equals CL on magnitude of C. For that matter, if you want to find CL, then CL will be equal to magnitude of C times the cos of the phi, and that is what we have here. Moreover, the height of the parallelepiped CL is equal to this. And for that matter, you can see that the base area of the parallelepiped is equal to area of the parallelogram, with A and B being the adjacent sides. So base area of the parallelepiped. Now let's check. This is the base area here. And then area is A cross B, or A, where vector A and vector B are the adjacent sides of the base of the parallelogram. And then base area, we can say that is the cross product of A and B. The magnitude, the area is the magnitude, or area equals magnitude of the cross product of A and B. Now we know that volume is the base area, which is of course this side here, the whole of this side. The base area times the height of the parallelepiped. And we have already concluded that the height of the parallelepiped is magnitude of C cos phi. And for that matter, the base area is already magnitude of A cross B. So you have A cross B times magnitude of C cos phi. Now, by the dot product theorem, we know that magnitude of A cross B times the magnitude of C cos phi equals to the A cross B dot C, which is from the dot product theorem. Okay, so we can see that the magnitude of A cross B dot C is equal to volume of the parallelepiped with the conterminous edges A, B, and C. For that matter, the scalar triple product A cross B dot C represents the volume of the parallelepiped whose conterminous edges A, B, and C are vectors. Okay, now let's look at an example here. So with this example, we have to find the volume of a parallelepiped with three adjacent sides formed by the vectors this and that. So we have already established that A cross B dot B, A dot into brackets B cross C can be written as this side, as this. So we find the magnitude as usual. So here we use the rule, which is the plus minus plus here. So we maintain our 3, we delete all entries to the right of 3 and beneath 3. So we will be left with negative 6, 4. So 3, negative 6, 4, 0, negative 2, minus. So minus, the next number is 1. All entries to this right and this. So we'll be left with negative 1, 4. So we have 1, negative 1, 4, 3, negative 2. Then we have the next one is plus, which is 5 here. So we have 5, and then we delete entries to this one. So we are going to have negative 1, negative 6, 3, 0. So 3 into bracket, negative 6 times 2 is 12, minus 0, 0 times 4 is 0, minus 1 into brackets. Negative 1 times negative 2 is 2, minus 3, 4, 12, plus 5 into brackets. Negative 1 times 0 is 0, 3 times negative 6 is negative 18. So here we have 12 minus 0 is 12, 3, 12, 20, 3, 12, 36. And here too we have negative 10. So negative 1 times 10 is positive 10. And then here too we have 5 times negative 18. So 5, 8, 4, 0, and 4, 5, 1, 5, So negative 90. So we have negative 90. And so 36 plus 10. Sorry, 36 plus 10 give us 46. And then here we are going to have negative 90. Sorry, I think there was a mistake that I made here. This one is negative, sorry. So here is negative. So we are going to have positive 90. For that matter, when we add this to this, we are going to get 100 plus 36, and that gives us 136 cubic units because it's volume. So cubic units. Okay. Volume of a tetrahedron. Another interesting aspect of our lecture today is how to find the volume of a tetrahedron. And how does a tetrahedron looks like? A tetrahedron is a solid with 4 vertices, P, Q, R, S, and 4 triangular faces, as shown here. So we have 4 vertices. We have 4 faces as well. So the vertices are 1, 2, 3, and 4. And these vertices are represented by O, P, R, S. And we have adjacent sizes, which are A, B, C, which are all vectors. And there is a unit vector which is also perpendicular to C, which is perpendicular to BC. Okay, so there is a unit vector which is perpendicular to the direction of B and C, for that matter, this one and this. So we are saying that the volume of a tetrahedron is 1/3 of the distance from the apex. So 1/3 of the distance from the apex to the opposite face times the area of that face. For that matter, we know that from triangle OSR, so OSR, the triangle at the bottom, the area is equal to half times the magnitude of B cross C. So this and this, the magnitude, half of the magnitude, that's the area for the triangle at the bottom. Again, the height of the tetrahedron is equal to this one times the unit vector, which is perpendicular to B and C. Okay. Moreover, finally, we are saying that the volume of a tetrahedron equals 1/3 times the base area times the height, and the base area is this, and then the height too is this one. So we are going to have 1/3 of half of magnitude B and C times A dot N. Okay. So since the magnitude of this is 1, then it means that this will be omitted, because 1 times this one will give us this one. So we are going to have 1 times 1, which is 1, 3 times 2, which is 6. So we are going to have 1/6 of the magnitude of A dot B cross C. Okay, now let's take a question on this. So calculate the volume of a tetrahedron whose vertices are at the points this. So the first thing to do here is to find the cross product. So here we are dealing with PR, PQRS, and for that matter, our PS, we are going to subtract. So the question is, how did we get this? So we used, the question is in PQRS, but here we are using AC, AB, and AD, of course, which makes it very difficult for us to understand. So the proper way is to be PR dot PQ cross PS. So PQ cross PS. So that is it. Now PR equals OR minus OP. So OR is 1, 1, 2 minus OP, which is 1, 1, 1. So we subtract this, we are going to get 0. This one too is 0, and here will be 1. So we are going to have K. For the rest, IJ are all zeros. Then the next one is PQ. So PQ is equal to OQ minus OP. And then OQ is 1, 2, 3. And then OP is 1, 1, 1. So subtracting each one 0. So 0, 2 minus 1 is 1. 3 minus 1 is 2. So it means that the I part of the vector is 0. So we left with J plus 2K, because here is 1 already. The last one we want to find is PS. So PS is equal to OS minus OP. So our OS is 3, negative 1, 2 minus P, which is 1, 1, 1. And for that matter, 3 minus 1 is 2, negative 1, negative 1 is negative 2. 2 minus 1 gives us 1. So we are going to have 2I minus 2J plus K, because here is already 1. Okay, so that is what we have here. Okay, so we have 2I minus 2J plus K for the last one. Now we arrange the three results here. Then first one we had 0, 0, 1, so that is what we have here. And then the second one we have 0, 1, 2, so 0, 1, 2 is also here. And then we have 2, negative 2, 1, and that is what we have here too. So by the determinant approach, we have our plus minus plus here, of course, which is we maintain the 0 here. Then we delete entries to the right of 0 and beneath 0. So we are going to have 1, 2, negative 2, 1. Then the second one to the same thing, but that is minus. And that we are going to have this one deleted, and then this one, so we left with 0, 2, and then 2, 1. And we have the last one to be 1. Then we delete all entries to the right of the left of 1, and here to beneath it. So we have 0, 1, and then 2, negative 2. So 0 times 1 times 1 is 1. 2 times negative minus 2 times negative 2, which is negative 4. And so we are going to have this one for the first one. Then we have the bracket 0 times 1, which is 0, minus 2 times 2, which is 4, plus 1, 0 times negative 2, which is negative, which is 0, minus 2 times 1, which is 2. So we are going to have 0 times the whole of it will give us 0, 0, and then this one will give us negative 2. So the final result gives us negative 2. And so when we take 1 out of 6 of negative 2, we are going to have 2 on 6. This is an absolute value, so we have it as positive. So we are going to have 2 on 6. And then when we simplify 2 on 6, we are going to get 1 on 3. And then convert 1 on 3 to a decimal. We are going to have 0.33, repeating decimal. And so we are going to have 0.333 cubic units as the volume of the tetrahedron. Thank you very much, and don't forget to subscribe to our channel.